Hi guys, welcome back to part 3 of our multiple regression lecture. So at this point we've looked at the pie sales example, we pulled out the coefficient estimates, and we even went ahead, interpreted them, and made a prediction. Okay, but I kind of want to take a look at what we've done and assess it, basically judge it and say, hey, is this equation that we came up with, so if I go back to that previous slide, this equation that we came up with, which summarizes the relationship between price, advertisement, and sales. So is this equation doing a good job at making predictions? Okay. In order to do that, judge it, I need to have a couple tools. So we're going to get into some of these tools. There are many tools, and I'm going to focus on a few. Okay, so before we do too much in the way of prediction and estimation with our multiple regression equation that we learned, we should assess it to see whether it's performing well. Building prediction models is oftentimes a process which requires many iterations. So it's not just a science where you just where everything is kind of clear cut and you just follow a sequence of simple steps and get an outcome. There is an art to this, okay? And so if someone's actually trying to predict something, they are going to spend a considerable time and try different versions of models to try to predict what they're after, okay? So the overarching goal in prediction modeling is to come up with good predictions, obviously. But we should keep our model lean. Lean meaning don't include predictors, independent variables that are redundant, superfluous, or irrelevant. We don't want to include, for example, two variables that give us the same information about our y variable. And we don't want to include variables that have nothing to do, no logical connection to what we're trying to predict. Okay, so we want to keep our we want to come up with a good model, a good prediction equation, but we don't want to have this thing become too big, filled with too much fat, if you will, unnecessary independent variables. Okay, so we may be trying to predict the pie sales, and in the process of building a prediction model like our multiple regression model that we just ran, we'll try various predictors. Each time we do that, so each iteration, we could try a different subset of the x variables that are available to us, all in the effort to predict y. So you might actually go through many versions of model building before you settle for one that you want to start using to make predictions. Okay, so here are some of the tools that we're going to look at to assess these models. So Rsquare, so something happened with the superscripts here. Hopefully it didn't mess up my subscripts, but we've seen R-squared before many times in simple regression, so it's not completely new. So that's actually a superscript, so it's r to the second power. Then we have something called adjusted R-square, and then we have two hypothesis tests that we're going to also look at. So we're going to look at these 4 assessment tools in this section. So first off, R-square, which stands for the coefficient of multiple determination when it's used in multiple regression. So denoted R-square, just like in simple linear regression, and some software oftentimes labels it like this. So just be aware of the different ways it's labeled. It still pretty much tells us the same information that it did in simple linear regression. It reports the proportion of the total variation in the y variable that's explained by, this time, not just one x variable, but all the x variables that we've considered taken together. Okay, so it tells us how well the independent variables are doing at predicting y. And it puts it into a number that ranges from 0 to 1, so it's easily converted to a proportion, so we can really relate to it and understand what it's telling us. Obviously, we would love to have an R-square that's close to 1, which would tell us that almost 100% of y is being explained by our independent variables. But oftentimes, we might be very happy to even see an R-square of 60, 70%. Okay? So it's all contextual. It depends on the type of problem we're working with, the type of research we're doing, and so forth. But one of the shortcomings of R-square is that it always increases as we add more x variables. It always tells us that things are getting better. Prediction power is getting better when we make the model bigger, meaning we add more independent variables, more x's. And if you remember the principle I talked about in the previous slide, we want a model that does a good job in prediction, but that's lean and not over bloated. So this is so if we just used R-square, we would always think that the bigger model is in question is better than the smaller model. Okay, and that's a problem. So R-square is a good tool to understand basically to interpret in this fashion for a specific model, but it's not a good tool if we're trying to decide between different models we've created on the same data. So for this reason, we'll still use it in interpreting a particular model, but if we're ever in a situation where we need to compare between two models, we'll have to have another tool. Okay, so here is where you can actually get this number from the output. So R-square is given to us in Google Sheets and in Excel. At the very top of the summary output, when we run the multiple regression, and in this example with the pi cells that we were just looking at, we went through the coefficients already. Here's the second piece of output that we're going to focus on, R-square, which was 52.15 if we round to 4 decimal places. So we can interpret this as 52.15% of the variation in pi cells is explained by the variation in all the x's. What were they? Price and advertising. So this is the interpretation of this number. And also, by the way, I give you how you can actually calculate this on your own using some of these other values. Okay, so you could look into that if that's interesting to you. It also explains what some of these other numbers down here are. Okay, so in this particular example, 52, about a little more than 52% of the variation in how many pies we're going to sell is explained by knowing the price that we charge and how much we spend on advertisement. So not the best R-square, but still informative. Okay. Now we get something called adjusted R-square. And adjusted R-square solves that problem that I explained a couple minutes ago. Okay, so R-square never decreases. So we remember that from the previous slides when we add new x variables. So add another x variable to the model. R-square will always tell you that things got better, even if it's a little bit. Okay, so that's not good if we're trying to come up with a good multiple regression equation so that we can make good predictions, and we have a couple different options and we want to compare between them. R-square wouldn't be the way to compare between them. When we want to compare between models on the same data, we use what's called adjusted R-square. And what adjusted R-square does is it adjusts R-square. So how does it do that? So we'll get to the actual equation first here. Let's just on a high level understand that the net effect of a variable, adding a new variable, is what we're interested in. So what the question that we need to be asking is, did this new x variable that we just added have enough explanatory power to offset making the model more complicated, more big? Okay, that's the question we want to ask. And so adjusted R-square will help us. So it shows us the proportion of variation in y explained by all x variables. Up to there, that's the exact same interpretation of R-square, except it goes on to say adjusted for the number of x variables used and the sample size. So basically, as you use more x variables, there's a penalty it's going to charge. There's a cost. So it's going to pull down R-square as you use more x's. The only way a new x will pull adjusted R-square up is if the cost of adding it is less than the amount of information that it adds to the model. Okay, if you can imagine that. Okay, so here you see R-square is in this equation, except we do a lot of adjustment to it. Okay, so have a bigger sample size, that will also make adjusted R-square increase, but since we're going to be using the same data, that's not going to really change for us. What's going to change is k, which is the number of independent variables. So if k goes up, that means we're using more x's in the model. We're making the model bigger. Okay, so there should be a price, and so this is the price for that. Okay, so it penalizes excessive use of unimportant independent variables. It's always going to be a little smaller, sometimes a lot smaller than R-square, plain R-square. Okay, and its usefulness, I should say, stress this one last time. The usefulness of adjusted R-square is when we want to compare among models, specifically on the same data. Okay, so let's take a look at the adjusted R-square from our pie sales example. So it's right under the R-square. So we pull it out. As you see, it's slightly less than R-square, a little more than slightly in this case. So let's interpret it. 44.2% of the variation in pie sales is explained by the variation in price and advertising. And then we add, taking into account the sample size and the number of independent variables. So the formula for adjusted R-square takes these two things into account, whereas plain R-square does not take those two things into account. Okay. Next tool, so we're in our third kind of assessment tool, the overall Ftest. So is the model significant? That's the question that this test will ask. It's a hypothesis test, as you can kind of see. The Ftest for overall significance of the model shows if there is a linear relationship between all of the x's and considered together and the y variable. Okay, so here is what it boils down to. It's the hypothesis test down here. The null hypothesis is that all the slopes are equal to 0. If you think about it, if you go back to the simple linear regression days, when we looked at a scatter plot, and the scatter plot kind of looked like this, and we looked at this, we gave this a name, we called it a null plot, or we said, in other words, there's no relationship between x and y here. Because look what happens. As I move along the x-axis, what happens to y? Nothing really, right? So if I were to summarize these points, I would come up with a flat line. What's a flat line? What's the slope of a flat line? Slope of a flat line is 0. So having a slope of 0 is another way of saying that there's no relationship between this guy and this guy. Okay? The only difference or complication here is that in multiple regression, as we've seen, we have multiple slopes. One slope for each of the independent variables. That's why you have beta 1 here, beta 2, all the way up to beta 3 equaling 0. So we're saying all of the partial slopes are equal to 0. In other words, there is no linear relationship between the x variables and the y variable. Okay, that's what HO is saying. The alternative hypothesis is saying that at least one of these guys, at least one of these partial slopes has a slope not equal to 0. In other words, it could be negative, it could be positive. It's just not this situation where there is no relationship. So in words, at least one independent variable affects y. Okay? So this is the hypothesis test. To answer a hypothesis test, obviously we need to know what alpha is, and then we need to know what the p-value is. If we know what alpha is and we know the p-value, we can make a decision either to reject HO or to fail to reject HO. So that exactly is the same as all the hypothesis tests we've seen before. Okay, so let's go to the output and see where we get the p-value for this test. So there's a few things associated with this test, but the p-value, it all culminates in this number. Okay, so the p-value for the overall Ftest in the pi-sales data that we just looked at was 0.01201. Here are all the numbers that build up to this guy. Okay, so if you want to understand how we get F, you can kind of follow this equation, but really all we need here is 0.01201. And so depending on what our alpha is, we would make a decision. So if I go back, so let's remember this number. Let's go back. So if I set alpha at 5%, which is a typical level of significance, my p-value was 0.01201. I got that from the output. Okay. Obviously, alpha is greater than my p-value, or you could say my p-value is less than alpha, which would cause me to reject HO. In this case, if I reject HO, I can strike this if I like to make it clear for myself. I have strong evidence that H1 is true. And what does H1 say? H1 says that at least one of these slopes, beta 1, beta 2, beta 3, so on and so forth, is not equal to 0. Okay? In other words, there is some meaningful linear relationship between the x variables and y. So let me actually make this more specific for our pi-sales example. Since we only had two predictors, we only had two partial slopes. So let me actually write the specific hypothesis test for our example. So we don't have k predictors, we have just two. So that would be the null. The alternative would be the same. At least one of these guys up here, beta I not equal to 0, and I would be either 1 or 2. And since I told you to use alpha of 5%, you would then make the decision we did down here. You would reject the null. Okay, so I wanted to be more specific for our data, our example that we did. This was the general template for this overall Ftest. Okay. Obviously, if you have 3 predictors, there would be a beta 3 here. If you had 4 predictors, there would be 4 betas here. If you had just 2, it would be like ours. Okay, so you shouldn't just write this guy when you actually know how many predictors you have. Okay, that's interesting. So basically, our conclusion from this assessment tool is that there is at least one independent variable that affects y, that has a significant linear relationship with y. Okay. Okay. So we follow up the overall F-test with what's called individual T-tests. If you reject HO in an overall F-test, what you've concluded is that at least one of the independent variables has a linear relationship with Y. But you still don't know if they both do or if just one of them does. And if so, if it's just one, which one of them? Okay? At this point, all I know is that price and advertisement have, at least one of those guys has a linear relationship with sales. So individual t-tests will allow me to then go a little more granular and see which exactly of the independent variables has a linear relationship with Y. So if I have two predictors, two independent variables, I'm going to end up doing two of these tests. If I have three, I'll end up doing three of these tests. Okay? So the question it asks is, are individual predictor variables significant? So we're going to use t-tests of individual variable slopes. Shows if there is a linear relationship between the variable xi and y. So one at a time. Okay. Here's the hypothesis test. HO is the particular variable has a slope of 0. So no linear relationship between xi and y. And the alternative is that there is a significant linear relationship, or it does exist, between xi and y. Now we're going to obviously fill in the blank for I. Okay, so for us, we're going to need to do two of these for the pie sales data. We're going to do one for advertisement. Okay. And maybe it would make sense to label this advertisement. Actually, price, I think, was what we called one. So let's stay consistent. Price, and then do a separate one for advertisement. So we'll have HO beta 2 equals 0, H1 beta 2 not equal to 0. And we'll use an alpha of 5% typically, but you should always look to the problem to see what alpha you should use. So here are the two t-tests for our pie sales data that we've been working with for a while. So here's the one for price, here's the one for ads. These are the tests set up. Now we go to get the p-values for each of these and make decisions for each of these separately. So let's go to the output. To get the p-value for the price test, we go to the row called price and we go all the way over to a column called p-value. And here is the p-value for that first individual t-test. Is that less than 0.05? Yes. So we would reject HO. Then we go to advertisement. We go over, and here is the p-value for the slope of advertisement. Is that less than 0.05, less than alpha? Yes. We would also reject HO there. So the individual t-test for a pie sales example, we had two independent variables in our pie sales model, so we performed two t-tests, one for each. Here are the two tests that I wrote a little sloppily. Here are them much more clearly. Okay, and by the way, here are the decisions that we just came to together. Here are the p-values that we just pulled out from the output, the computer output. Okay, and this is the reason why we reject. Okay. This is the reason why we rejected for advertisement. So our conclusion in all this is after performing both individual t-tests using the appropriate p-values provided up to us by our computer software, there's evidence that both price and advertising affect pie sales. Or you could say both price and advertising have a significant linear relationship with pie sales. Okay, so that rounds up the 4 assessment tools that I'm going to discuss. In the final part of this sequence on multiple regression, I'm going to teach you how to handle categorical independent variables. Because up to now, everything we've been looking at in regression has dealt with numerical, quantitative variables, both for the dependent and the independent. Well, it turns out that we can actually use numerical variables as well as categorical variables for the independent variables, okay? But we require some pre-processing for that. So in the final part of this video, this sequence, I'm going to show you how to handle categorical variables.